Hello, my name is Jared Skeens and welcome to the Zoom room. Today we'd like to look at the new mechanics test for the May-June 2020 series. Again, the 2020 is the new syllabus year. And so this is the first of the 2020 May-June series for mechanics, which is paper 41. So paper 4, zone 1. And you can see it is still an hour and 15 minutes long, and it is still a 50-point paper. So let's look through it and see what we have here. Here we have 3 coplanar forces of magnitudes 100 newtons, 50 newtons, and 50 newtons act on at a point A, as shown in the diagram. The value of cosine alpha is 4/5. So right away, we need to resolve forces, and in order to resolve forces horizontally and vertically, we need both sine and cosine. So to get sine, remember cosine is adjacent over hypotenuse. So the 5 is the hypotenuse. So we can use the Pythagorean theorem and work backwards. So 5 squared minus 4 squared, that's 25 minus 16 is 9. Square root is 3. That gives us the opposite side. So sine alpha then is 3/5. So we can figure that out really quickly. And since 3, 4, 5 is a triplet, very common triplet, you could probably mentally do that without using your calculator. Find the magnitude and resultant of the 3 forces and state its direction. So in order to do magnitude and resultant, we need to resolve our forces. So here we have going to the left, 100 Newton force. And since it's already on the x-axis, we don't really have to resolve it. Then to the right, we have a 50 Newton times alpha, cosine of alpha, which is the 4/5. So 50 times 4/5 is 40. And we have another one on the bottom with the same magnitude and same cosine value because it's going to the right, the adjacent side. So both of those come out to 40 newtons. Then for resolving vertically, we have a 50 going up. So that's times the sine, which is the opposite side, sine alpha, which is 3/5. So 50 times 3/5 is 30. And then we also have the same thing going down, 30 newtons going down. So when we combine these into a resultant for the horizontal forces, the 100 is larger, so we put that first, minus the 240s. So that gives us 100 minus 80, which is a 20 Newton force in the negative x-axis direction to the left. And when we resolve the forces vertically, it comes out to 0. So in other words, they're completely balanced, the up and down forces. So that leaves us with a resultant force with magnitude of 20 newtons, and the direction is in the negative x-axis direction. So how you describe that with words, as long as you have the same idea, you can say it a couple different ways. But magnitude of 20, direction to the left or the negative x-axis, you could probably even say the 180-degree direction. On to question number 2. A car of mass 1,800 kilograms is towing a trailer of mass 400 kilograms along a straight horizontal road. The car and trailer are connected by a light rigid tow bar. The car is accelerating at 1.5 meters per second squared, and there are constant resistant forces of 250 newtons on the car and 100 newtons on the trailer. Find the tension in the tow bar. So here is our horizontal road, and here we have our car with the big box and the trailer with the little box. And we have an unknown driving force pulling the car forward. And so I just put a question mark there. We have tension in the tow bar that pulls both ways. the trailer pulls against the car pulls against the trailer. So our tension goes inward on the tow bar, but outward from each respective object. And then we have our resistance on the cars, 250, and resistance on the trailers, 100. So again, remember with these connected particles, you can treat the system as a whole, in which case you would ignore the tension in the middle, or you can do each of the objects separately. And since we need to solve for tension, we can't use the whole system because that wouldn't use the tension. And we can't use the car because we don't know the driving force yet. So we use the trailer, and we know that since there is an acceleration, then the net force for the trailer will be mass times acceleration. So the mass is 400 times acceleration. That's the Newton's law. And then the net force, or the resultant force, would be the T minus 100. The T comes first because that's the direction of our motion. So T minus the 100. And when we work that out, we get 600 for the net force. And for tension, we ended up with 700 newtons. Now that we know the tension, we can put those values in for T. And moving on, it wants us to find the power of the engine when the speed is 20 meters per second. Well, we know that power is force times velocity. Well, we have the velocity. Now what we need is the force. And this force is referring to the force of the engine. In other words, the driving force, which is what we didn't know up here. But now that we have the tension, we can figure it out. So again, we use mass times acceleration for the car. 1800 times 1.5, that gives us the Newton's law net force. And now on the right-hand side, we do our resultant forces. So our force due to the driving force minus the forces of resistance, which would be the 700 of the tension and the 250 of the resistance. So both of those forces are resisting the driving force. So that gives us 2,700 equals the driving force minus 950 newtons of total resistance. And so the driving force has 3,650 newtons multiplied by the velocity of 20 gives us a power of 73,000 watts. You could also put 73 kilowatts as your answer if you want to. Number 3, a particle is projected vertically upwards with a speed of 5 meters per second from a point A, which is 2.8 meters above horizontal ground. So here's our picture on the right. Here's our horizontal ground. Here's point A, 2.5 meters above the ground. And from this point, we have our particle P projected upwards with an initial velocity of 5 meters per second. So find the greatest height above the ground reached by P. Well, of course, if P is projected upwards, at some point it's going to come to a stop at the highest point, and that's where the velocity will be 0. So we use our Suvat formulas here. V squared equals U squared plus 2AS, because we want to find that height above A. So our final velocity will be when it reaches 0. Our initial velocity is 5. So U squared equals V squared equals U squared plus 2. A is our acceleration due to gravity, which is pulling downwards, pulling in the opposite direction, so -10. And then times the distance, and distance is what we're solving for. So when you work this out, you end up with a distance of 1.25 meters, and you need to remember that was from the point of perspective of A. So the 1.25 is how far P goes above A. The question asks for the height above the ground, so we need to add that 1.25 to the 2.8, and to get the maximum height there of 4.05 meters. Then down to part B here, find the length of time for which P is at a height of more than 3.6 meters above the ground. Well, let's start with what that would be above A, because A seems to be our best reference point. So 3.6 minus the 2.8 is 0.8 meters above A. Well, A, we know, had an initial velocity of 5 meters per second. We now have a distance above A to work with, and we have our acceleration. So we can find what the velocity would be at that particular point. So again, we use the v squared equals u squared plus 2as. Well, now our s is a specific point that we're looking at, 0.8 meters. We solve for that, and we get the velocity at that particular point to be 3 meters per second. So now we can figure out the time that it takes for particle P to get from 3 meters per second all the way to the top, which is 0 meters per second. So we just use v equals u plus at, where v, again, our velocity at the top was 0. Our initial velocity being from respect to this 3.6 meters above the ground, or 0.8 meters above A, is 3 meters per second. Acceleration, again, from gravity is -10, and we're solving for the time that it takes. And when we solve that, it takes 0.3 seconds to get up. So we need to multiply that by 2 to include the time for it to get it back down to that 3.6 or 0.8 meter mark. And so we have a total of 0.6 seconds for which particle P is above 3.6 meters above the ground, or 0.8 meters above A. Question number 4, we now have a ring on a rod, horizontal rod, with a ring of mass 0.1 kg threaded on a fixed horizontal rod. The rod is rough, so that means you're going to have to deal with friction, and the coefficient of friction between the ring and the rod is 0.8. A force of magnitude T newtons, which we can see here in the diagram, acts on the ring in a direction 30 degrees to the rod downwards in the vertical plane. Initially, the ring is at rest. So find the greatest value of T for which the ring remains at rest, meaning our system is in equilibrium, because at rest means no acceleration. So equilibrium means the forces are balanced. So first we need to find our force of friction with respect to the variables or the information that we have. So force of friction is mu times the normal contact force. Well, it gave us the mu, the coefficient of friction, 0.8. Our normal contact force will be the force going up that counteracts all the vertical forces going down. So the forces acting down on the ring are the 1 Newton, which is from its own mass, mass times acceleration. So 0.1 times 10 is 1. As well as over here, this force pulling at the 30-degree angle also has a downward component of T sine 30, which is a half T. So that means our force of friction in terms of T is 0.8 plus 0.4 T when you distribute that through. And when we look at the force going to the right, so the force of friction is going to the left, the force pulling to the right, that is the horizontal component of this T Newton force, is T cosine 30, that's the adjacent side. And so cosine of 30 is 0.866 T. Now we can balance our forces in terms of T. So the tension then that would keep this system at rest is 1.7167, or to 3 significant figures, 1.72 newtons. So that's our tension that will keep it in equilibrium. Moving on, now it wants us to find acceleration when the t is 3. Of course, if the tension is 1.72 and it's in equilibrium, if you increase that force, then the ring is going to start to move, and once you get that movement, you then have acceleration. So we want to find that acceleration of the ring when t equals 3. So now that we have acceleration, we have Newton's law. Our net force is mass times acceleration, with a being our variable. And then we resolve the forces to horizontally. So we get the 3 cosine 30 minus the friction, which was 0.8 times 1 plus half t. Well, now our t is 3. So plugging in the 3's, we get resolve the right-hand side, or resolve the forces going to the right, 0.598. Divide by the 0.1 gives us an acceleration of 5.98 meters per second squared. Going on to question number 5. Here we have this interesting diagram. It's a child of mass 35 kilograms that's swinging on a rope, and the child is modeled by particle P. So here's the child at the end of this 45-meter rope, swinging in this circular pathway from this center point up here. And the rope is 4 meters long. P is initially held, so that would be at rest, at a 45-degree angle to the vertical, which shows it in the diagram. Given that there is no resistance, find the speed of P when it is traveled halfway along the circular arc from its initial position toward the lowest point. So I just put a dot here approximately halfway in the middle, which would mean our angle then is 22.5 degrees, or cut the angle in half, plus this 45 degrees up here. So what we need to realize here is, even though it's asking for speed, normally with velocity we would use suvat, but suvat is for straight line type questions. Here we have a uniform motion along a circular pathway. That automatically means there is acceleration. So since there is, and our acceleration is going to be changing, a changing acceleration. So we can't use suvat, we can't use calculus because we weren't given any position, velocity, or acceleration function to work with, and we can also not use the net force and Newton's law. So what that leaves us with is to, instead of using those kind of formulas, to use like an energy and energy type equations. So we can figure out height and use potential energy. So if we find our initial height below the horizon, notice if it's 45 here, it's also 45 over here. So our initial height below the horizon, solving that where the hypotenuse is 4, gives us 2.8284 meters below the horizon. So the second height, which would be at our halfway point here, would be the 45 plus the 22.5, and solving for that gives us a height of 3.6955. So you have to add those two angles. You get 67.5, sine of 67.5 times the hypotenuse 4 gives that 3.6955. So our loss in potential energy, because we're dropping height, is 35, that's the mass of the child, times gravity is 10 over a height difference. Now remember, potential energy is not affected by a change of horizontal position. It's only affected by a change in vertical position. So the circular pathway does not matter. What matters is the change in vertical height. So we get 303.625 joules. So that's a loss of potential energy. Since there is no resistance in this particular question, then that means the potential energy is equal to the gain. The loss of potential energy is equal to the gain in kinetic energy. So for kinetic energy, we have 1/2 mass v squared minus 1/2 mass u squared. And our initial velocity was 0. So that just leaves us with this term over here. So 1/2 35 v squared, multiplied the 2 to the other side, and then divide by 35 and then square root, gives us a velocity of 4.16 meters per second at that halfway point. The next part of the question now says there is resistance, and the work done against resistance to the lowest point, the work done to the lowest point from its initial position is x joules. The speed at the lowest point is 4 meters per second. So what we want to find is how much work was done against resistance from the initial held position at 45 degrees all the way to the lowest position, which is in the straight down vertical direction. So we need to find our change of height again. So since our rope is 4 meters long, then in the straight down direction it's 4 minus the 2.82, which was at the 45 degree mark, gives us a change of 1.1716 meters. So now our loss of potential energy is 410.06 joules. Our gain in kinetic energy, because we now know the velocity of 4 meters per second. Again, the initial was 0, so that kind of cancels out the second part. So 1/2 35 times 4 squared gives us a gain of kinetic energy of 280 joules. So in this case, our potential energy does not equal the kinetic energy. We lose some of that potential energy to the work done against resistance. So in other words, not all of that energy is converted to kinetic energy. So we have the 410 joules of potential energy. We have the 280 joules of kinetic energy. So now we can solve for the work against resistance that is lost from the change of potential energy. Solve it, add it to the other side, subtract the 280. So our work done against resistance comes out to 130 joules to 3 significant figures. Question number 6. A particle moves in a straight line AB. The velocity v after t seconds of leaving A is given by this equation. V equals k times parentheses t squared minus 10t plus 21, where k is a constant. The displacement of the particle from A to direction B is 2.85 meters after 3 seconds, 2.4 meters after 10 seconds, or sorry, 6 seconds. Find the value of K. Hence, find the expression in terms of T for the displacement. So it wants us to find the displacement, which is the position vector. It gives us the velocity as a function of time. So what I did is I distributed the K through, and then we integrate from velocity to the position function. So that means you add 1 to the exponent, divide by that number. So you follow your integration rules, you get through the end. Remember, this is an indefinite integral, so we add c at the end. And that's why we have 2 different values given for us, because we need to find k and c. So we need simultaneous equations. We plug in our 2.85 for the position with a 3 for the time. So 3 cubed is 27, divided by 3 is 9. 3 squared is 9 times 5 is 45. And 3 times 21 is 63. So we have all of these now in K plus C gives us 2.85 equals 27K plus C. If we do the same thing with our 2.4 and 6, Plugging those in, we end up with an equation of 2.4 equals 18k plus c. We subtract those two equations. I subtract going in the upwards direction so that I end up with a positive value. 0.45 equals 9k, divide by 9, k equals 0.05. Plugging that back into one of our previous equations gives us a c of 1.5. Now we want to put that all together into our position function in terms of time, our displacement function here. So the k now can go out front just like it did here. And we need to remember that that factors it back out. So we have our 1/3 t cubed minus 5t squared plus 21t. However, notice that k was not ever a part of c. So you need to be a little careful here how you finish off this position statement. The k can go out front. The k comes out of these three. So you have a choice. You can either put the parenthesis after the 21t and then leave the c as a plus 1.5. Or what I did is I just factored that 0.05 out of the 1.5 and you get 30. So I just included it all in the parentheses, but I had to change my c value because of the k being factored out. So there are a couple of ways that you can do it, but you want to be careful how you handle that c because the k was never a part of it. Now part B, find the displacement when its velocity is a minimum. So minimum is the first derivative set equal to 0. So the first derivative of velocity is the acceleration function. So derivative, you multiply to the front and subtract 1. You do the derivative, set it equal to 0, solve for t, you get 5 seconds. Plug that back into your position function that you just solved for in the previous part, and you end up with a position or displacement after 5 seconds being 2.58 meters. Now here at the end, question number 7, this happens to be the new syllabus material for 2020. It has to do with momentum. And so this is what the new momentum questions will look like. Here we have a particle of mass 0.3 kilograms lying on a smooth plane inclined at 30 degrees to the horizontal. It's released from rest, so that means its initial velocity is 0. P slides down the plane for a distance of 2.5 meters, then reaches a horizontal plane. There is no change in the speed, meaning the horizontal plane is smooth also. The particle Q of mass 0.2 kilograms lies at rest on the horizontal plane 1.5 meters away from the end of the inclined plane. So all of that's shown in the diagram. P collides directly with Q. So your key word that this is a momentum question is this collision, and it is given that the horizontal plane is smooth, which is why there was no change in velocity. After the collision, P continues moving with a speed of 2 meters per second. Find the speed of Q after the collision. Well, first we need to find the acceleration of this object going down the hill, and so that we can find its final speed. So since there is acceleration, mass times acceleration is 0.3a, and we need to resolve the force going down the plane. So that would be 3 sine 30. We'll resolve our force horizontally parallel to the plane. So remember, this 30 degrees is also in your little resolving triangle. And so you get 3 sine 30, which is 1.5, and divide by 0.3. So our acceleration is 5 meters per second. Now we want to find the velocity of particle P when it reaches the bottom of that inclined plane. It was released from rest, so it's 0 squared, v squared equals 0 squared plus 2as, where a is 5 and the distance 2.5. So our velocity squared is 25, meaning the velocity is 5 meters per second. And since the horizontal plane is smooth, then there is no resistance, and particle P will continue at 5 meters per second along the horizontal plane. So with momentum, there is a conservation of the mass times velocity. So particle P is 0.3 mass times 5 velocity, plus particle Q is 0.2 mass with no velocity because it was at rest, gives us a total momentum of 1.5. That needs to be conserved after the collision. So it's said that particle P at 0.3 kilograms continues to move at 2 meters per second. And so our 0.2 mass for particle Q times its velocity, which is what we're solving for. So subtract the 0.6 over, you get 0.9 divided by 0.2, means particle Q will continue on with a velocity of 4.5 meters per second after the collision. Now they have a follow-up question. It is given instead that the horizontal plane is rough and that when P and Q collide, they coalesce and move with a speed of 1.2 meters per second. So now we have a change to the context. Our horizontal plane is now rough, which means there's going to be a reduction of velocity as P moves across that horizontal part. So we need to recalculate the velocity of P. And they coalesce, meaning after the collision, the two particles become one particle. So find the coefficient of friction between P and the horizontal plane. So now it's asking us to find the friction. We know there's friction because it's rough. They want us to find the coefficient of friction. So what we're going to want to do here is we're going to want to work backwards from our coalesced momentum with the speed that it has and work backwards so that we can find that friction. So if our particles coalesce, then that means the 0.3 plus the 0.2 join together into one particle, traveling at a velocity of 1.2 gives us a total momentum value here of 0.6. So that 0.6 had to have been conserved. That's the 0.6 after the collision, needs to be conserved before the collision. So remember our Q was at rest, so that means our particle P, 0.3 times V, then slowed down to a velocity of 2 meters per second. So now we can calculate its acceleration over that horizontal part, because the initial velocity when it got down that inclined plane was 5, and when it reached particle Q was 2, so V squared equals U squared plus 2AS, and we know that that distance along the horizontal was 1.5 meters that was given. So we plug those in and we solve for the acceleration as a negative 7 meters per second squared. The negative means it's decelerating at 7 meters per second squared. So now what we want to do is find the net force. So the net force, again, Newton's law is mass times acceleration. So 0.3 times 7. We don't need the negative. The negative is directional. If you put it in, it wouldn't really matter. So you get a total of 2.1 newtons. The negative would simply mean that it is going against the direction of motion. So what we really need here is the absolute value, because we're looking for the mu, or the coefficient of friction. So 2.1 newtons is the value of the force divided by 3. Now where do we get the 3 from? If you come back up here and look at the diagram, the particle P has mass 0.3, so times 10 gives it a 3 Newton downward force. So our normal contact force by this horizontal surface back up against particle P will also be 3 newtons. So that's our normal contact force, is the 3 newtons pushing back up against particle P. So we plug that in for normal contact force, which gives us a mu of 0.7. And that ends our first mechanics test for the May-June series of 2020, the new syllabus. I hope this is helpful. And again, thank you for joining me in the Zoom room, and look forward to seeing you again next time.